So one of our last topics is finding area and volume using integrals. So before we jump into that, let's review a topic from just the beginning of when we learned about definite integrals. So if we have this curve, and the curve is called f, we know that we could, if we want to find the area under the curve, from A to B, so there's A to B, we know that we could break this up into small rectangles. So if we subtract B minus A, that gives us the width of that entire interval that we're considering. And then if we divide that by n, where n is the number of subintervals, what we get is delta x, and we said delta x represents the width of each subinterval. All right, so when we consider an individual rectangle in here, we said that we find the area by multiplying its height times its width. So in the case of this first rectangle, we could think of it as like the ith rectangle, so it could be any rectangle. The height would be the function at that point, and the width would be the length of that little subinterval, our delta x. So if we want to approximate the area of the region, we said that we can basically add up all of these rectangles. So for each rectangle, starting with I equals 1 until we get to I equals n, we're going to multiply the height times the width. And we said that when we do this and we add those all up, this is what we call a Riemann sum. So again, that just gives us an approximation for the area because we're literally just adding up rectangles. So all of that is just a geometric understanding. But what makes this calculus is when we then take the limit. So if we consider the limit as n approaches infinity, that means that we basically have infinite rectangles and they're infinitely small. Or I guess we should say infinitely narrow. So this delta x, we said this is called the differential. This becomes infinitely small. And then we said that because n is approaching infinity, that means we're going to have infinite rectangles. So it's the limit that makes this calculus. So when we look at the relationship between the definition and the actual integral itself, the stuff that is inside of our sum here, we said that becomes the integrand. And so our delta x becomes dx. And then the function we would just write as f of x. And then our limits of integration, we said that just tells us the width of the original interval that we're considering. So as we jump into what we're going to talk about today, let's keep that in mind. In this unit, we're going to, trying to get that back in view. We're going to work with finding area between two curves. So not just the area under one curve. And I'm going to highlight some stuff on here that I'm going to erase afterwards. So feel free, you don't need to highlight this unless you want to, but I'm going to erase it. So if we were to just integrate from A to B, if we were to integrate the function f, if we did that, we would get the area from A to B that's under the curve of f. I'm using the highlighter so it's not super precise. but it would give us this entire area that I'm highlighting blue. All right, so that's what we get from integrating f. If we integrate instead under g, so from a to b, integrate the function g, that's going to give us the area under, I should say between the function g and the x-axis. So it gives us that bit. So if we want to know the area between the two curves, there's kind of two ways of thinking of it. We could just subtract the top minus the bottom, because when we find that top area, we get all of this other junk that we don't want. So we could think of it as just subtracting those two, or what we could think of instead, I'm going to erase that highlighting, is that each of these rectangles, that the height of each of these rectangles is just the f value, so the height of the function f at this particular value of x, minus the g value. So top minus bottom gives us the height. So just like before, we said every rectangle is a length times a width, but now we could think of the ith rectangle, so just some rectangle, that its height is going to be top minus bottom. And then the delta x, again, we said that's the width of the subinterval. So just like we did before, we said we could approximate this area with a Riemann sum. And starting from where I equals 1 to I equals infinity, we're going to add up all these rectangles. Their height is f minus g, and their width is delta x. So again, that's just an approximation. The thing that makes it calculus is now applying this limit. And again, this limit is going to give us infinite rectangles, and they're going to be infinitely narrow. And so we just arrive at this definition again. So we said anything in a box is really important. I don't know that we need to memorize this, but we need to understand this idea is that if we're integrating between two curves, the height is always going to be top minus bottom. And I'm sorry, I started thinking about something else. I'm not going to go there right now, but yeah, so we'll just say top minus bottom. And the rest of this is just the same. So we could either literally subtract g from f, we could apply our properties of integrals to evaluate them separately and then subtract. But this is going to be the main idea that we work with in this first part of this unit.